Welcome again to our Jyväskylä Summer School. So today is our fourth session, and the topic for today is Moiré electronic states in twisted van material. So before we start with the actual physics part of the session, let me start reminding you what is the schedule for today. So first we will have again 40 minutes lecture, then a 15 minutes break to get some air and also to think about something. More 40 minutes lecture, 15 minutes break, and then finally 40 minutes lecture. All right, so the plan for today is essentially to go through different emergent states that appear in Moiré materials. And in particular, we are going to deal both with the nature of Moiré physics and its relation to quasi-periodicity, then how Moiré electronic structures appear, first with regards to the one structure folding, unfolding, and the emergent electronic states that we get in minibands. And then we are going to see what happens in these minibands and how these Moiré effects actually impact the properties of materials. In particular, in terms of how Moiré effects increase correlation in the van der Waals materials, how they allow to create topological states. And finally, we are going to discuss some very specific type of twisted van der Waals materials, which are twisted graphene layers. So in terms of materials, today we are going to be thinking about a different set of twisted van der Waals structures in general of Moiré structures. So maybe the simplest type of twisted van der Waals material that we can think about is just twisted bilayer graphene. So this heterostructure in which we put two layers of graphene, one on top of another, and as we change the angle, we get different Moiré states. But what is important to note is that we can actually have many other different types of Moiré states, and we actually can even have Moiré states with a single layer. So we don't need two layers of a van der Waals material. We can just take one layer and get a Moiré state. And this is, for example, what happens if you take a single layer of graphene and you put it on top of a substrate, and graphene gets spontaneously buckled. So sometimes the buckling is periodic in space. So the buckling itself acts as a Moiré potential and gives rise to minibands in a single graphene monolayer and even to correlated states in a single graphene monolayer. And then, of course, apart from typical correlated states and Moiré states in twisted graphene multi-layered, we can also have very similar physics in other twisted van der Waals materials that are semiconducting, and in particular in transition metal-like alloys. So these materials include, let's say, MOS2, MOSE2, tungsten disulfide, tungsten diselenide, and so forth. And essentially, you can combine different of these two-dimensional semiconductors on top of another and also create different Moiré electronic states. And then finally, what is also important to note is that Moiré effects are not only important for the electronic degrees of freedom, namely the electronic bond structures of actual electrons, but they can actually have a very, very strong impact in materials that are not insulators, that have a charge gap, and that in principle you could think that it doesn't affect too much the electronic properties. And maybe one of the paradigmatic examples of this is the case of twisted magnetic two-dimensional materials. So essentially, by layers in which you take two MOS insulators, you can think about chromium chloride or chromium bromide or chromium iodine, any insulating magnetic material. You put it on top of another at a certain twist angle, and this twist angle actually severely impacts the magnetic properties of the material and even creates a new electron quarter. All right, so today we are essentially going to focus on how to understand the electronic properties of these first three types of materials, but I'm going to briefly tell you a little bit about this last case. All right, so first of all, let us remind ourselves how we can create Moiré states in twisted van der Waals materials. And I think that this is maybe one of the most unique features that we have in two-dimensional materials. So, of course, all the phenomenology that we saw in the previous session, like superconductivity, magnetism, and so forth, also appears in three-dimensional compounds, and also appears if you grow, let's say, a single unit cell of a two-dimensional compound on top of a substrate. But the emergence of Moiré states is actually intrinsic of two-dimensional material, and it actually stems from the very weak chemical forces between the different layers of your two-dimensional material. So the first important idea to remember is that in two-dimensional materials, we can combine any two-dimensional material with any other one, irrespective of the lattice constant. And this irrespective of the lattice constant is actually the key for getting Moiré space. And then apart from that, we can of course also change the angle between the two materials. And this capability of changing the angle allows us to have control on the length scale at which the moiré appears. So let's start with the simplest example of the moiré that we already discussed in the first section. So the basic idea is to take two layers of the material with four components. We can take graphene, one on the left, one on the right. We put them one on top of the other at a certain angle. And if this angle is non-zero, there's a pattern in space that repeats itself. This pattern in space is what we call the Moiré structure. And the length scale of this pattern is what defines the Moiré length. And this Moiré length is going to define a new superlattice that in the case of twisted bilayer is essentially characterized by the length scale at which the AA stacking in the graphene bilayer repeats itself in space. And then, of course, if you color all the parts of the space in which you have AA stacking, you essentially have an emergent superlattice with a lattice constant that is controlled by the twist angle between the layers. And as we discussed in the first section, if you take just this simple twisted van der Waals multilayer, this twisted bilayer graphene, just by changing the twist angle between the two layers and by changing the electric bias between the two layers, you essentially realize a huge variety of electronic phenomena. So for example, here, you can recognize that you realize both superconductivity and correlated insulators and churn insulators, some of the electronic states that we've been discussing in the previous sessions. But apart from that, we also can realize different types of topological states, topological network, fractional churn insulators, and of course also churn insulators. And thanks to the Moiré, you can even see quasi-crystalline that in principle you cannot see in a single monolayer. So the idea to remember is that this idea of combining different two-dimensional materials and changing the twist angle between them is something that not only applies to graphene, but applies to all the two-dimensional materials that we have. So you can essentially take any of the two-dimensional materials that we've been discussing in the previous section, put it on top of any other one, put it at a certain angle that you want, and see how is the electronic structure that is obtained in this situation. So just as a reference, from this whole family that it is of course not even complete, today we are going to focus on the case of graphene, tungsten diselenide, and yeah, and that's all. And of course, other semiconductors that are diphosphogenates. But you can play this very same game with all these other two-dimensional materials. So let me start with a very simple twisted Moiré heterostructure in which the phenomenology is actually very easy to understand, even without understanding the electronic structure of twisted Moiré systems. So the basic idea is to take actually two layers of a multi-insulator, two layers of chromium chlorine or chromium iodine or chromium bromide or any two-dimensional magnetic material that you have. Some very interesting property of these two-dimensional magnets is that if you focus on a ferromagnetic one, each layer is ferromagnetic within itself, right? So all the atoms, for example, in chromium bromide or chromium iodine point in the same direction because of the exchange coupling that we were discussing yesterday. But when you have two layers, the magnetic alignment between the two layers can be either ferromagnetic or can be anti-ferromagnetic, right? There's nothing that tells you that it has to be one or another. Of course, the coupling is going to depend on small details of the electronic structure, in particular, on what is the effective exchange coupling between one layer and the other layer, but in principle can be either ferromagnetic or anti-ferromagnetic. The, let's say, very lucky feature of these materials is that this exchange coupling is actually extremely sensitive to details, and in particular is extremely sensitive to the actual alignment between the two materials. So if you just take a bilayer of, for example, chromium bromide or chromium iodine, and you displace it a little bit with respect to the other one, you can change the coupling from ferromagnetic to anti-ferromagnetic. And this displacement is what is actually usually called a change from monoclinic static to rhombohedral static, which it is just a lateral displacement of one layer with respect to the other one. This is, of course, a picture in the case in which two layers are perfectly aligned. So if you have two layers perfectly aligned, just by slightly sliding one with respect to the other, you can go from a ferromagnet to an actual ferromagnet. And when I say anti-ferromagnet, I say anti-ferromagnet in between the layers. Each layer is, of course, ferromagnetic by itself. So now if you think about a twisted 2D magnetic material, of course, the twisting angle is going to create different stackings in space. So in certain parts of your moire, you're going to have the rhombohedral stacking. In other parts of your moire, you're going to have the monoclinic stacking. What this actually means is that in some parts of your moire, the coupling is going to be ferromagnetic, and in other parts of your moire, the coupling is going to be anti-ferromagnetic. So essentially, in certain parts of your moire, the magnetization of the two layers is going to point in the same direction, and in other parts of your moire, the magnetization is going to try to point in opposite directions. And if you now take, let's say, a certain path from a point in which the coupling is ferromagnetic to a point in which the coupling is anti-ferromagnetic, well, you know that in one of the regions where the coupling is ferromagnetic, the two layers are going to be pointing in the same direction. In the part in which it is anti-ferromagnetic, they are going to point in the opposite direction. And of course, in the middle, something must happen. And in particular, you're going to get some non-collinear magnetization. So in other words, just by taking two materials that are ferromagnetic by themselves and twisting them, you create a magnetic system that has non-collinear magnetization, starting from materials that only have collinear magnetization. And of course, something that may already come to your mind from the previous lecture is that if you have a two-dimensional material that has a non-collinear magnetization, if the non-collinear magnetization is changing direction in the right way, you may actually get a ferroelectric polarization just from this non-collinearity. Just remembering this formula that we discussed yesterday. So we have a Q vector that essentially tells you in which direction the magnetization changes. We have a spin rotation axis, and if this cross product is non-zero, we essentially get an electric polarization. So in other words, you start with a two-dimensional magnetic material that has collinear magnetization, and when you twist two of this, you get two things. First one, non-collinear magnetization, and the other one, ferroelectric order, starting from a material that doesn't have any of the two.
It depends on whether it's near or block or.
Yes, exactly.
So which one actually gives the, I mean, has to if the rotation is within the same plane as the spin, then there is no polarization. So, and then if rotation is out of the plane.
Yeah, so let's say this one gives rise to polarization. So the E vector is perpendicular to the plane, and then the Q vector goes in the,
okay.
Right. So you always need that the E vector is perpendicular to the Q vector.
Yeah.
Let's say. So if you were rotating like this, then it would be the wrong one. Let's say
the block wall. Right.
Yeah, I get it. Yeah, right. Yeah, great thing. That was a very important. Yes.
And it doesn't always happen in one layer, or in both simultaneously. Like on the picture, it looks like it's just happening in one of the layers.
Yeah, that's a very good question. And the answer to that is it depends on how the exchange couplings are actually. So, I mean, this picture that I put here was just a sketch to show you that if you go from permanent to anti-permanent, somewhere you're going to have a non-collinear magnetization. But of course, it could happen that the non-collinear magnetization appears in both layers, or that in some regions of, let's say, your moire, it appears on one layer, and in other regions, it appears on the other layer. So that is something that depends on the specific details of the Heisenberg Hamilton, of course. Yeah, great. That was a very good point. All right, great, wonderful. So I think that this is a very simple example in which just you can see that the moire in a two-dimensional material is right to just emergent behavior, even without thinking too much about the electron structure. So just thinking in terms of local couplings and how local couplings change your properties in space. All right, so that is everything that I want to tell you about moire in motion later. So now let us move on to actually understand what is the impact of moire states, and in particular, quasi-periodic potentials in the electronic structure of systems. And for that, we are going to start discussing about something very much related, which is the notion of quasi-periodicity. So to make things, let's say, as simple as possible, let us just think about one-dimensional moire potentials. And let me emphasize that everything that we are going to discuss about one-dimensional moire potentials also applies to two-dimensional Moiré potentials, but this will allow us to visualize all the phenomenology in a much easier way. So let's think that we take, let's say, two different materials, have different lattice constants. So we have one material on top, one material on the bottom, and since they have different lattice constants, we are going to have a modulation in space of the parameter of the Hamiltonian. And for concreteness, let us assume that the material on top is a metal, so it has electrons close to the chemical potential, and the material on the bottom is a semiconductor or an insulator, and the impact that creates is to modulate the potential that electrons feel in the top layer. So a very simple Hamiltonian that we can break down that essentially models this phenomenology is essentially this one. So we consider that we have just an orbital per side in the top layer, and those electrons have just hopping, and let's say that just first neighbor hopping, and then since we have another layer below that creates a potential that is modulated in space, we can model that as an on-site energy that depends in space, and it has a certain wavelength, and the wavelength is what we call Q. Now, the bottom line is that, of course, if you take a random value of Q, in principle, the potential that you are going to get is not going to be commensurate with your lattice. And in particular, if you take a value of Q that is 2 pi times an irrational number, then you are never going to repeat the same potential ever in space. If you take a value of Q that is Q times a rational number, eventually that potential is going to repeat itself. So let us just see what happens to the electronic structure once we start adding this potential that in general is going to be incommensurate with the lattice, and that it's going to have a certain specific strength. So this is essentially the spectra that you get for the one-dimensional model as you change the value of the frequency of the modulation. So this wave, Moiré wave number is the Q that you had in the previous equation. So the basic idea is that you see a fairly complex spectra. Let me emphasize that in this system, before you had the Moiré potential, you had just a single band. You had a continuum of states from the bottom of the spectra to the top of the spectra. And now, once you switch on a certain Moiré modulation with a certain wave number, you suddenly create a set of gaps in your electronic spectra. And the number of gaps that you have depends on the wave number of the modulation, which in terms of Moiré material means that it depends on what is the twist angle between the two materials. And in general, you get a relatively complex spectra, and actually in the limit in which the potential is incommensurate, you get a fractal spectra. So you get an infinite number of gaps, an infinite number of bands. And what is most interesting is that these gaps here are topological by themselves, and they are very much related to the quantum topology. So if you think about this picture, you may actually have seen this picture in a relatively different context, which is the concept of electrons in a magnetic field. That is something that we are going to discuss tomorrow. So when you put electrons in a magnetic field, and you look at how the electronic states are as you ramp up the magnetic field in 2 dimensions, you get exactly this very same spectrum. So in other words, you take a 1-dimensional electron gas and add a Moiré potential, and you get the very same spectra as in a 2-dimensional electron gas when you add a magnetic field. What this actually tells you is that some of the properties of 2-dimensional systems are inherited in a 1-dimensional system with a quasi-periodic potential. So this is usually what this actually means is that 1-dimensional quasi-periodic systems actually reflect 2-dimensional physics, and in particular 2-dimensional quantum Hall states. And of course, you can keep playing this game over and over and over. So if 1-dimensional quasi-periodic potential reflects 2-dimensional quantum Hall states, 2-dimensional quasi-periodic potential reflect actually 4-dimensional quantum Hall states. And if you could create 3-dimensional quasi-periodic potential, they would reflect 6-dimensional quantum Hall states. So of course, we cannot create 3-dimensional quasi-periodic potentials, but we can create 2-dimensional quasi-periodic potentials. All right, so that's
the question with this picture that is the center here is kind of the case U equals 0, and then that means that there's just constant potential, so nothing happens.
Yeah, so
So the original spectrum is there.
yeah, so Q equal to 0 is here, this is Q equal to 5.
I see, okay.
Yeah, so this is
The
Q equal to 0,
the
Q equal to
original spectrum is at the edge.
oh yeah, this is because it's a finite.
Yeah.
Essentially. But of course, if you make the system bigger and bigger, you have the same
Yeah.
picture.
Yeah.
So yeah, this is Q equal to 0, which means just a constant potential. Then Q equal to pi, and Q equal to 2 pi, which is simply Q equal to 0. All right, great. So the first idea to keep in mind is that a Moiré potential or a quasi-periodic potential is going to create many gaps. And these gaps are actually already topological by themselves because they are related to a two-dimensional problem. Then the next idea that is also very interesting to keep in mind regarding this model is the following. So in the previous picture, I was showing you how the spectra depended on the weight vector of your modulation, keeping the amplitude of the modulation constant. So now let's do the opposite. Let's keep the weight number constant. So now we have a modulation that has a certain weight vector in real space that in general is going to be commensurate with the lattice, and we are going to ramp up its value. So if we take a value of the potential equal to 0, we essentially get a continuum of states. So this is what we expect for an infinite system. So we have a band structure, and that band structure is described to a continuous density of states. But now, as we start ramping up the potential, we start generating these gaps. So in particular, you see that you generate gaps whose value becomes bigger and bigger as the value of the potential becomes bigger and bigger. And here, what the color that I'm using for the states is something called the inverse participation ratio, which is essentially the absolute value of the wave function to the 4th power. So let me emphasize that if you take here absolute value of the wave function to the 2nd power, you essentially get 1 because all the wave functions are normalized, all have normal 1. If you take the absolute value of the wave function to the 4th power, what you are actually seeing is how much the wave function is spread in space. So if a wave function is localized on a single side, the inverse participation ratio is 1 because 1 to the 4th power is 1. But if a wave function is very spread in space, and it's actually a delocalized state, the value of the inverse participation ratio is 0. So the inverse participation ratio essentially tells you if a wave function is localized or if it is extended in space. If a wave function is extended in space, you get 0, so you get blue. And if a wave function is localized in space, you essentially get 1 or a value very close to 1. So of course, in the absence of a potential, all your states are delocalized in the chain because you have block waves, and block waves essentially extend throughout the whole chain. So now you start ramping up the value of your quasi-periodic potential, and when you observe that your states remain delocalized, suddenly they completely change at a certain critical value of the potential, and afterwards they become completely localized. This is actually known as a critical quasi-periodic transition. What this actually means is that when the quasi-periodic potential is relatively weak, all your states are delocalized in the system. When your quasi-periodic potential is very strong, all your states are localized in the system, and then there's one point at which your states are critical. So in terms of the inverse participation ratio, or in terms of the wave function, what this actually means is that in one case, the weight of your wave function is, let's say, 1 over n, where n is the number of sites. So you have an infinitely large limit. You just have an extended state that lives everywhere. If you are in the localized limit, you have states that decay exponentially, and therefore can be normalized. And then in the critical case, you get states that decay as a power law. And what is actually very important from here is that critical states are states that are very likely to have enhanced electronic correlation, just because they decay as a power law and they can interact with each other very easily. So these critical states are actually states that appear relatively often in certain twisted van der Waals heterostructures. And in particular, if you start computing the electronic structure of a twisted van der Waals material, quite often you see very sudden transitions between states that are delocalized in the Moiré material to states that are fairly localized in certain parts of your Moiré. So now, of course, this picture of extended states and localized states is something that holds when your potential is quasi-periodic, when it never repeats itself in space, right? If you think about, let's say, every specific potential that repeats itself in space, of course, you would say that, well, the states are always going to be delocalized, because if there's a certain periodicity, there's going to be a certain length scale in which you can define a unit cell. And if you can define a unit cell, you can define block waves, and block waves are delocalized. So if it happens that your wave vector is commensurate, you would say that, well, your states are truly delocalized all the time. But what is important is that even in that case, you are going to see a very strong transition between states that are delocalized in your Moiré unit cell to states that are very localized in the Moiré unit cell, even if you have a certain periodicity.
Basically, if you would take n to infinity, this blue would just fade out.
Yeah,
the red would actually stay red.
Yeah, so the blue would go to zero.
Well, I guess it's white. Zero.
No, so the blue here is zero. So blue is zero, red is
Okay,
one.
what is white then between the
0.5. So here, you can.
Between the reds there is white region.
Yeah, so this is the color scale.
Okay.
So the blue would be 0, white 0.5, and red 1.
Okay, so there is finite weight of every energy also right. Because of white, I know that white means 0.
No. So yeah, sorry, I should have put the numbers here. So blue means 0.
Yeah.
That means that the IPR corresponds to a delocalized state, and red is 1, which means that the IPR corresponds to the most localized state. And then
Yes. But when you are on the right,
yeah,
and you have the red is the localized states. But then if you are at an energy between the red stripes, you still have some finite rate there. Right?
You mean here?
Yes.
Oh, here there are no states.
Yes. So how do I know then what is the difference between white and blue?
Yeah, I probably should have taken a different color, but this, I mean, this is not exactly white, but gray, let's say. So this gray appears here, let's say, and all the whites that you see are gaps.
Yes. So and you that's my point. If you take n to infinity, blue also becomes white because it becomes a gap. There are no, I mean, you cannot see anything there.
No, the blue states.
Going to infinity and you have 0. So how do you compare 0 to 0?
No, the blue stays blue because even if you take an infinite number of sides, your IPR is going to take a value that is 0 or at least 1 over n. Okay. So all these states are going to keep the blue color as you go to infinity.
But then you should color the gaps also blue, because it's a question of the blue spectral function basically. And if you have a gap, inside the gap of the spectral function is also 0.
Yeah, but this is actually not the spectral function. So this is just the eigenvalue actually.
But I think the IPR is something else than 0 inside the gap.
No, so what I'm doing here is I'm plotting the eigenvalue. So each eigenvalue is a point, and the color of this point is the IPR. Yeah. So if you see a point, then it means that you have an eigenvalue there, and then the color of that point essentially means what is the IPR associated with the eigenfunction of that eigenvalue. So white means that there's no eigenvalue there, and then either blue or red or gray means that there is an eigenvalue there. Okay. Yeah. But yeah, maybe this gray should have been green so that it can be seen more easily. All right, great. So this is something that we should keep in mind every time that we compute electronic structures of twisted van der Waals materials, that we can get very sudden transitions between states that are heavily localized in the Moiré itself and states that are very heavily localized in the Moiré itself. And this stems just from this critical transition in quasi-periodic systems. All right, great. So now let us move on to understand what is the electronic structure of a system that has actually a certain periodicity. So before we were thinking about quasi-periodic systems that have modulations that were incommensurate in space. But of course, when we compute electronic structure, we often cannot compute systems that are infinite and incommensurate, but we need to take a certain Moiré unit cell or a certain length scale at which the system is periodic so that we can compute band structures. So that is what we are going to do in the following. So again, let's start with the simplest system. So a one-dimensional chain, a one-dimensional electron gas. And again, we are going to take that we have just kinetic energy in this one-dimensional electron gas. And to start with, let's not put any more potential whatsoever. Let's just look at how the electronic structure is of this one-dimensional chain by taking, let's say, different unit cells. So of course, the most natural unit cell in a one-dimensional system is just one side per unit cell. But in principle, you could say that you have two sides per unit cell, and then your translation is two lattice constants, or that you have 6 sides per unit cell, and then your translation is 6 lattice. And in principle, the properties of your material should not depend on whether you decide that the unit cell is one side, or the unit cell is 2 sides, or the unit cell is 6 sides, because this is just an arbitrary definition that you make in order to solve the Hammond point. But any observable, any property needs to be independent of this choice of unit cell, because they all describe the exact same system. So let's start with the simplest choice. So one side per unit cell. So of course, in this case, the electronic structure is very simple, right? This is just a band structure of a one-dimensional model, and this is the typical cosine electronic structure that you get just from first neighbor Taiwan model. Now, if you take 2 sides per unit cell, now what you get is that instead of having one band, you have 2 bands, right? Just because your block Hamiltonian now is a 2x2 matrix, and a 2x2 matrix must have, let's say, 2 eigenvalues. And now you see that, of course, now that you have 2 eigenvalues, your band structure looks a little bit different. You still hope that it describes the same system, but now it's a little bit different. And of course, you can now take a unit cell with 6 sides, and we take a unit cell with 6 sides. Now you are going to have 6 bands. And just because, well, if you have 6 sides, again, your Hamiltonian is going to be a 6 by 6 matrix. And again, you hope that this describes very same system. So essentially, you have 3 band structures, 3 electronic structures that technically describe the same system, but they look a little bit different. So you have the band structure for a single side per unit cell, for 2 sides per unit cell, and for 6 sides per unit cell. And now the question that we want to answer is, how do we know, or how can we see that these electronic structures actually represent the very same system? So there's actually something relatively simple that we can. So if you think about the unit cell with 2 sides, what we can actually do is to, let's say, compute our band structure twice. And by twice, I mean going through 2 chromosomes. So the path that I showed you for the 2 sides was from gamma to X to gamma, but we can keep going throughout the reciprocal space, right? So we can take gamma to X to gamma, now the gamma in the next unit cell to X in the next unit cell to gamma in the next unit cell, and so forth. And in terms of band structure, that actually means that you repeat your band structure twice. So if the beginning and the end is gamma, you just have to kind of paste your bands twice, which is equivalent to going through the reciprocal space to 2 unit cells. And now, when you look at this band structure, you actually recognize that at least part of your states are the states that you had when you had just a single side per unit cell, right? So, and in particular, let's say this red band is essentially the bands that you had when you only considered a single side per unit cell. So this notion of repeating your electronic structure and picking the band that corresponds to the minimal unit cell, it's what it's called electronic structure unfolding, which essentially tells you that if you make a supercell of a certain material, you are of course going to get many additional bands. But if you repeat your band structure, let's say several times, which essentially means that you go through reciprocal space in several unit cells, and you pick the right eigenvalues, you essentially recover the very same band diagram that you had before. And this is, of course, something that you can do systematically, no matter how many sites you're going to sell, or in other words, no matter how big you chose your supercell. So for example, if you think about the band structure with 6 sites in which our unit cell had 6 different orbitals, then let's say the first Brillouin zone was essentially up to here, but if you now repeat it 6 times, you essentially see that you can select one band in each different Brillouin zone that when you paste together, gives rise to the original band structure with a single side unit cell. All right, great, wonderful. So now we know how to somehow read the original electronic structure from the electronic structure of a supercell. So now what we are going to do is we are going to break the translational symmetry of our unit cell. And the way in which we can break this translational symmetry is by adding a certain superpotential. In particular, let's just add a certain lattice of impurities. So we add an impurity at this point, we add an impurity 6 lattice constants away, then another one 6 lattice constants away, and so forth. So we essentially create a super lattice on top of our original crystal. So in this case, what we actually can do is just to compute the electronic structure in a unit cell that contains 6 sites, where one of the sites is the impurity. And now we just repeat this electronic structure several times throughout reciprocal space and see how we can recover our original structure in the simplest unit cell. So again, this is how the electronic structure looks like if we don't have any impurity. So if we don't have any impurity, we essentially are in the same crystal limit as we had before. And in this limit, we can, of course, just, let's say, see that our original band is this one. And now let me emphasize that one can, let's say, systematically know which is the band that you have to take, or what is the spectral weight of each eigenstate of the band that you want to take using this unfolding procedure. So this unfolding procedure is not just you picking by hand the band on the band structure, but it's actually a well-defined mathematical procedure in terms of spectral functions. And all right, great. So this is what we get from this unfolding procedure, where let's say the color essentially tells you what is the weight on the unfolding. So here, blue means that you have, let's say, 0 weight on your original unit cell, and red tells you that you have full weight on your original unit cell. So now if you add this lattice of impurities, so this superpotential, what you actually see is that you create anti-crossings in your bands. So if you had taken them just a single Brillouin zone, you would see, let's say, up to here, right? So you would see your 6 bands with anti-crossings in between the bands. But if you now start repeating your electronic structure several times in reciprocal space and pick the right eigenvalues according to the unfolding procedure, what you actually see is that your original cosine-like band got shattered in several parts. So essentially, you open gaps in different points of your original band structure, but you still have, let's say, relatively well-defined weights on your original, the block weight functions. So essentially, this is the idea of electronic structure unfolding. So you can see that when you have a superpotential for an electronic structure, you essentially open gaps in your original electronic structure, and in particular, you start creating new band tops and band bottoms on your electronic structure. And of course, this is something that you can do systematically. So you can now take different, let's say, super lattices and see how your electronic structure gets modified according to the lattice constant of your super lattice, or even in terms of twisted van der Waals materials, in terms of the twisting angle between 2-dimensional van der Waals materials. So as your wire length becomes bigger and bigger and bigger, you develop more and more and more bands, each one creating a new anti-crossing in your original electronic structure, and each one creating new band tops and band bottoms in your electronic structure. And now what is very interesting to note there is that every time that you create a new band top or a new band bottom in your electronic structure, you can add additional features to your density of states. So if you don't have any type of perturbation in your, let's say, in your unit cell, or in other words, if you don't have any type of super lattice, essentially the the density of states that you can have, it's relatively featureless. It's the density of the states of the original two-dimensional material that you have. But now, as you start switching on the magnitude of your superlattice, you start creating these band tops and band bottoms that give rise to their own density of states, or in other words, to their own Mann-Hoff singularity. So in other words, just by switching on a superlattice potential, you can go from a situation in which your density of states is very low to a situation in which your density of states is suddenly very big, just because you open these many gaps.
Question, like if you want to calculate it, like do you treat the superlattice like with perturbation theory, or how does the agnostic theory?
Yeah, that's a very good point. So if you take that your superlattice is, let's say, commensurate with your original lattice, you can just solve the whole problem exactly just by taking a very big unit cell. And in this case, for example, you take one impurity every 6 sites, you take a unit cell with 6 sites, and in that case, you can apply Bloch's theorem and solve the problem exactly. So you don't need to use perturbation theory. You just have to take the right supercell and just exactly solve that right supercell. And yeah, in relation with that, so what I'm showing you here is directly the, let's say, unfolded electronic structure, where essentially the weight is the unfolding, let's say, proportion here. So essentially, this directly allows you to see how the electronic structure in the original unit cell gets reconstructed. So this comes from an exact calculation, and you don't need to use perturbation theory. Yeah, thanks. That was a very nice point. All right, great. So that's the first thing that we learned from this Moiré potential, that they create new band tops and band bottoms, and they can substantially modify the density of the states of a system just by these electronic constructions. All right, so I think that now it's a very good time for a break. So I would suggest that we can take a 15-minute break. And again, you can go outside, get some air, but if you want to think about something, I would like to ask you to think about what is the value of the superlattice constant that we should take in order to have a periodic system. And I'm giving you, let's say, 2 different options. So the first option is just alpha to pi over L, where L is the number of sites, and alpha is an integer. And the second option, alpha pi over L. And yeah, we can discuss about this after the break. So I would say that we can start again at 10 o'clock. So yeah, see you at 10.
So in this context, commensurate is mean. In this context, commensurate is mean.
Commensurate means that you can define a unit that eventually the potential will be